I was quite happy when, I was playing with O1, which was like the first reasoning model, and it couldn't really answer things. I then started asking DeepSeek. So DeepSeek came out in January, took the world by storm because they sort of revealed that it's quite easy to train these reasoning models. Uh, Again, for the audience, a reasoning model is a language model that thinks to itself before it answers. So it just does some sort of thinking and then generates the answer. So DeepSeek came out, and I started asking the questions, and it looked kind of close to getting the right answer. Still not perfect, and it took a long time, but I was like, actually, you're thinking along the right lines here. And then O3 came out 2 weeks later, or O3 Mini, and all of a sudden it could answer questions that I just could not believe. I jumped out my seat in one of them. I was like, this is an insane, this question, like I could not solve it, and it solves it. So I created the benchmark just because I was like, everyone, like there needs to be attention here. These reasoning models can now think about the structure of molecules.
Hello, Nicholas. It's a pleasure to have you here today. Uh, I, I guess, first of all, welcome everybody to episode 13 of the Polling Principle. Uh, Thank you for being here. I think we've met maybe 6 months ago, 9 months ago. I don't even remember at a conference.
About then, yeah.
And then since then, I think, I mean, I'm sure you've been working on a lot of really interesting things, but the one thing that caught my attention was a paper that you published maybe a couple of months ago, talking about language models and how now they can understand chemistry a lot better. So I'd love to talk a little bit more about that. But to begin with, why don't you tell us a little bit about you and your background and how you got into this space?
Well, yeah, thank you very much for having me. So I'm Nicholas. I'm actually a chemist by training. So I did my undergrad at the University of Edinburgh in medicinal and biological chemistry. So that's a chemistry course focusing more on like medicinal biological type area. And then I started that 5 years ago. And around about during all that time, all the AI hype was happening. You were talking about AI this, AI that. I thought, well, maybe I'm a bit behind because AlphaFold came out, and I thought, oh, well, AI is solved. But I thought, no, no, I'll give it a go. So I started teaching myself as much as I could in my spare time while I was doing chemistry at the same time. And I had the most fantastic supervisor in Edinburgh, Antonia May. So we did a diffusion paper together right when diffusion was first getting hot. And so then finished my undergrad. I did an integrated master's. So I went to AstraZeneca for 1 year, worked in their AI team, uh, sort of computational chemistry, generative modeling for drug design on an actual drug project. And now I'm in Oxford doing my DPhil. DPhil is what Oxford refers to as a PhD. They call it DPhil because, of course, Oxford has to be different. But I'm in the Oxford Protein Informatics Group, supervised by Charlotte Dean, and not officially, but also Fergus Emery. My research now has turned into language models for chemistry and language models for drug discovery, which is maybe the last thing I ever expected myself to be doing. But here I am, and it's a cool world.
Yeah, yeah. I mean, you can think of it maybe training the last generation of chemists, right? With the AI-powered chemi.
It's possible. It's possible. Yeah.
Um, cool. So, maybe kind of to begin with, let's talk a little bit before about your previous work on diffusion, right? So, I mean, for people that are not familiar, right, like diffusion is kind of the same type of um method or algorithm that is used for image generation, very successful, right? I think it was
Mhm.
Mid Journey in like the 2022 or something like that time frame, the one that kind of they managed to get it to work properly. There's this idea of like, well, why don't you go ahead with explain it?
Well, it's been a few years since I've last done diffusion, so I'm no longer an expert or well versed. But yeah, diffusion models, they first became hot for image generation. Do you want a quick summary of how diffusion models work? I don't know.
Yeah, let's
Yes.
go for it.
Well, so the very simple idea is that diffusion models, you take your image and you apply noise for a few steps. So like each step, you're just adding a bit more noise, like destroying the image slowly. And you'll do that step by step for say 100 steps. Uh, and then what you're machine learning model is done is that you train to do the reverse process. So starting from pure noise, can you generate the image? Uh, and it doesn't sound like it should work. It sounds a bit silly, but then actually it works surprisingly well. So for the last few years, all the big image generation models were all diffusion models. Uh, and by analogy, you can think of molecules in a similar way. There's a bit more conditions, right? Molecules are three-dimensional and images are 2D. So you have to think about molecules in 3D, but the idea is the same. You take your molecule. Uh, at the time, it was just a very simple diffusion model where we took uh, molecules, took the atom coordinates and the atom types, apply noise to it. So you move the atoms around a bit in space, destroy the molecule slowly, get to pure noise, and then train the reverse, go from noise to molecule. And surprisingly, it worked okay. Wasn't like incredible, but also the models were quite small. So I think if you were to scale it up, maybe they'd be more powerful.
Yeah, yeah. If you had a cluster with
If
that,
I had infinite
you,
compute, that would
right?
be nice. Yeah.
Yeah. I mean, and I think it's interesting. Right? Like, I'm definitely far from an expert, but like my understanding is that with diffusion models, you can generate molecules that fit inside of pockets.
Mm,
But kind of better or faster, right? That with a lot of
yeah.
approaches.
So that was my project. So I actually, I'm not a person like a machine learner. I don't really train models that much. I'm more interested in how can we use them to solve interesting problems. And the problem that I was faced with was fragment-based drug design. So in this uh, type of drug discovery, you take your protein, uh, and then you take a small molecule that's just like a few atoms, like say like 10 heavy atoms, and you crystallize them together. So your chance of crystallizing a small molecule in your protein is quite high, much higher than a bigger molecule. So you get these small fragments, and it's almost like a jigsaw puzzle of how do you combine them together. So my trick was taking a diffusion model that was already trained. You can actually show it the fragments during the denoising process, and you sort of inject this information slowly as it's generating, and you end up generating molecules that look a bit like the fragments, but also look a bit more like a molecule. So it's a way to combine them together, like solving that jigsaw puzzle. And it worked like as good as you could expect for something quite simple. Uh, and then there's a newer paper that came from OPIG, which is a group I'm in, Mole Snapper, which does a similar idea, but for the protein. So you move coordinates with respect to where the protein is. Again, like there's no like conditional training. You're not training models to do anything new. You're taking a model that already exists and doing some smart things with it.
Very interesting. Very, very cool. Which I guess is eventually is what you want to do, right? Like,
Mm.
an AlphaFold model can give you like you know, I guess, where that molecule would fit if it fits, inside of the protein. But eventually what you want is probably to come up with a new molecule that you don't know about, right? Like, let me have a better fit, right? So I guess it's, maybe, still beyond a lot of the state of the art model today.
Mm.
Um, cool. So let's talk a little bit about language models, right? And
Yeah.
and what they can or can't do. So like how did you start thinking about language models doing chemistry? Was it, did you start about thinking about the benchmark first, or was it, like let's see what we can do? Or
Yeah, the story is weird, right? So ChatGPT comes out, was it 3 years ago now? And it's kind of cool. And then it gets better and better and better. And then about a year ago, it was better than me at doing chem informatics. And like I've been doing chem informatics for like 4 years now, so I'm by no means an expert, but I'm also not a novice. And it is far faster at coding and can do really complex stuff. So there's a realization at some point that it's possible to reach human level capabilities in certain tasks. And I was always wanting sort of to be able to speak to a language model to do chemistry, but they weren't really able to answer questions in the way that I was hoping. You ask a question, it's like, well, it's a bit stupid. And uh, I think the key problem was that they just didn't seem to understand this property of molecules, that molecules are graphs being nodes and edges connected to each other. And so it just seemed like it had this like fundamental misunderstanding. And then we also met a few months ago. I need to apologize to you because you pitched this idea about language models to me. And I didn't believe you in the slightest. I thought there's absolutely no way that language models could solve the problems that you're talking about. And I now believe that they can. Um, not necessarily easy, uh, but it seems possible based on my results. And just based on what I'm seeing, it's like there's been a step change yet again, and maybe quite soon they'll be able to do some quite advanced things.
There is this, I would say, I mean, I didn't believe initially, right? I got convinced by other people, but there's this thing that happens in computer science that does not happen in other fields, which is we get exponential curves of like, productivity or power or different techniques, right? And of course, every computer scientist, has known about, Moore's law and the compute capacity of chips, right? And how it, keeps getting faster and faster and faster, right? So when you go and pick somebody in the 80s and tell them this is a Motorola chip, it has like, 8,000 transistors and it can compute, additions or whatever. And then, you tell them this thing, is going to, fly airplanes by itself or whatever one day, right? Like it's very hard to imagine that, right? But once you have seen enough exponential curves, it's like, well, it doesn't matter, how good it is today, right? If it's improving, 10% per
Mm,
month, right? Like, within a couple of years, this thing is going to be incredible, right? And I think it was fairly obvious that that was going to happen to language models because there is so much strong commercial interest, right? Like, you can use them for so many things that are useful in real life. So it's like, well, it doesn't matter if the model, can understand 1% of chemistry questions right now, because next
mm,
month is going to be 2%, and then a year from now will be 20, and then 3 years from now, like we don't even need to like, worry about it anymore, right? So I mean, I don't know. It's a very natural way to think about it for a computer scientist, but it doesn't happen in any other field that I know of, right? Like it's not like in chemistry you get people twice as productive this year than last year, right? Or like in like my favorite example is like automotive engineering, right? And how like sometimes you tell people, well, could you take a mechanical engineer and design a car in one afternoon? And I was like, makes no sense, right? But that's what computer scientists do, right? You pick up computer science and build me a web server with an app and then some interaction and a database, and like, how long would that take? Or, one afternoon of work,
mm,
right?
mm. It's yeah, it's a pretty cool world. It's so fast paced, and like there's a sort of collision that happens with chemistry. So like as a chemist, I'm a chemist, right? And yeah, there's this conflict that scientific research is just inherently slow. It takes so long to be in a lab, and I think people also forget just how hard it is to synthesize a molecule. You spend at least a few days, but probably weeks and maybe months in the lab synthesizing a molecule. So whilst it's easy for a computing scientist to come up with a pretty cool, like innovative AI model, you have to uh, always remember that the scientist in the lab that's working really, really hard and give them the respect that they deserve. And really, like and it's our duty to do a really good job uh, because I don't think it's well. There's this problem that exists in the world of AI right now that computing scientists will come up with like really cool AI algorithms for chemistry, but then they don't really work or they don't solve a problem. And then they try and say, "Oh, we've solved it. We've solved drug discovery." And then like the chemists in the lab are like, "No, you haven't," and they sort of get offended, and it's just annoying. It's such a shame. It's like maybe it's because machine learners just have to have this hype world, right? It's just like they have to be the best.
You have to have things to raise money from
Yeah,
investors, right? Let me tell you that.
yeah, yes. So I'm doing my best to try and bridge that gap and remember as much like do the highest quality chemistry I can do,
Yeah.
whilst also bridging the gap and getting the best machine learning stuff as well.
I mean, like, maybe we'll talk a little bit more about that too, right? Like, there are so many open problems, right? Like, within chemistry, I think, and once you go maybe beyond that into like, biology, I think, there are, many, many years of interesting, work ahead.
Many years ahead of us for sure. There's so many problems. Yeah.
Um, cool. So, like, I think one of the things that you found in the, there's a couple of things of this that I want to touch on, right? Like, so what you found in the paper was, maybe some of the models can answer a few questions relatively, easily. And then, once you get into like, the O3 and like, more powerful models, and their accuracy increases, much, much more.
Mhm.
Right? Like, I think it was like, they were like, 50% or 60% of the questions they answered correctly. Um, and I think you kind of make the thesis that it is the reasoning of those models, what kind of enables them to do that. I mean, as I was, as I was going through, I was thinking, well, like I said, is it reasoning, or is it tools, or is it you just have more training data set? Like, well, what are the kinds of, how are these things, different, right, from each other, right? Like, and what are the things that enable these models to actually understand chemistry a little bit better?
Mhm. Mm. So, just for the benefit of the listeners, I'll summarize what my paper is. Um, so, yeah, I went in with this uh, sort of problem that I didn't believe language models could understand molecules, and I'm pretty confident like this is the key thing about chemistry. Is one unifying principle is that you need to understand the structure of molecules and talk about the structure of molecules. Uh, and all other chemical reasoning, at least for organic and inorganic, is dependent on that graph-based reasoning. So I constructed this benchmark of 8 different tasks that ask different questions about molecules at different levels of complexity. We use a smile string. Smiles is a text representation of molecules. It's just sort of a standard that we use in cheminformatics. And I asked some very simple questions of like, how many carbons are in this molecule? Which sounds easy. It's actually not as easy as you might think, but it's still relatively easy. It's just counting. And I got a bit more complicated, like a smile string, because it represents a graph, we can ask graph questions. So what's the shortest distance between 2 points uh, on the graph? So you'd have to count along the atoms, and maybe for rings, it gets a bit confusing because you have to go backwards. And I got up to the most complicated question, which I had was NMR elucidation, which for the non-chemists, it's NMR elucidation is a classic like problem that you give to a first or second year of uh, almost like molecular Sudoku. Here's all of these constraints and information that you get from the spectrum. You have to generate these hypotheses, piece it together, and then generate a molecule. So I asked all these questions at different levels of complexity. And I started this because I was like, well, language models obviously cannot do this. And they couldn't. And I was quite happy when, I was playing with O1, which was like the first reasoning model, and it couldn't really answer things. I then started asking DeepSeek. So DeepSeek came out in January, uh, took the world by storm because they sort of revealed that it's quite easy to train these reasoning models. Uh, Again, for the audience, a reasoning model is a language model that thinks to itself before it answers. So it just does some sort of thinking and then generates the answer. So DeepSeek came out and I started asking the questions and it looked kind of close to getting the right answer. Still not perfect. And it took a long time, but I was like, actually, you're thinking along the right lines here. And then O3 came out 2 weeks later, or O3 Mini, and all of a sudden it could answer questions that I just could not believe. I jumped out my seat in one of them. I was like, this is an insane, this question, like I could not solve it, and it solved it. So I created the benchmark just because I was like, everyone, like there needs to be attention here. These reasoning models can now think about the structure of molecules. Not perfectly. They're not particularly efficient at it. Like, it's not like this is a replacement or like the most optimal way to solve these questions. But the fact is, yeah, the models, they can answer these reasonably complicated questions reasonably successfully. Uh, and yeah, the O3 mini model was run without tools, without any agent stuff. So it's just the model by itself thinking through the problem.
Mhm.
Um, and so yeah, I wanted to see like what's going on here. At the time, it was only ChatGPT was like really the only model that could answer the questions. I'm going to start benchmarking some more models. That's my plan for tomorrow. So see if this holds true for other models as well. But at the time, it was only O3 Mini that could do anything. And we obviously don't have access to any of the behind the scenes. So we don't know what it was trained on. But there is one nice option. There's 3 reasoning modes. So you can select how hard it thinks. So you say thinks low, medium, or high. And all that does is just determine how long the model thinks for, sort of uh, how hard it thinks. And that's like the best control that we could have possibly done, I think. And we show that as you increase that reasoning parameter, the success rate goes up. So it seems like reasoning longer resulted in greater success. So that's why I'm making a claim that more reasoning is better.
Yeah, yeah, yeah. I mean, so you mentioned a lot of very interesting things. I mean, one of them is like we don't really know what is happening underneath, right? I think people, uh, kind of stop publishing all the details about their papers. Maybe except like DeepSeek, right? Which is very, I guess, gracious. Talking about how they actually did that. OpenAI definitely didn't, right? And I think all the other reasoning models they don't really share much about like how they are actually building the data sets and how they're doing their trading and so on. I guess maybe now that there's a little bit more competition, right? Like people don't want to reveal all their secrets. Uh, but yeah, I mean, I think letting the model process things for a while longer and come up with this, long reasoning chains seem to work for some other things. I personally, I think a little bit more partial to when the models can run tools, they become a lot better suddenly. And for coding, like this is very obvious, right? Because you can generate the code and run the code and see the error and then iterate, right? Uh, and if I remember right, I think somebody said that some of the ChatGPT models, some of the recent ones, they can now run um are they Git? Yes, interplay, right?
Yeah, that was a fun update. So yeah, my paper came out, the preprint. It's not published yet, but the preprint is out. And then a week later, OpenAI add RD kit to ChatGPT, which I didn't. I don't know why I didn't expect it, but it was just it was clear that the models like we know the models can write RD kit code, and the reasoning tracers would say to themselves, "Oh, I'm trying to run RD kit, I don't have access." So someone's just pip installed RD kit, and now it can run it. It was quite nice for me. So I I always like knew about agent models as well, and I think it's quite an obvious sort of solution. Is that well, the model can't do this directly; it struggles to count, but so we can write the Python to count.
Mhm.
So it's very tempting to get the agent model to just use RDKit, but the same problem still stands of like, if you can't somehow navigate the molecular graph and you can't reason on the graph, then you still won't be able to do chemistry. And I haven't done benchmarking of the agent models, but it just based on like preliminary, like me playing around, it it doesn't seem like these models are inherently better at understanding structure of molecules, but they are able to do more things now because they can write the code and execute it.
Yeah, very interesting. Yeah, I mean, like I don't know. It's this funny thing. Um, I have a rule that outside of the AI field, there is this test prompt that people have been using to kind of evaluate model, which is how many R's are in the word strawberry. How many are yeah. Yeah, so like it's I think it's I mean it's funny, right? Because like any human that understands a little bit of language, like a kid, can answer
Mm.
that question, right? But language models struggle for reasons, right? Like, the way they do tokenization, right? So things are maybe not necessarily split or whatever. Uh but of course, like one, quick easy way to get any model to answer that correctly would be like, or like current models do, like just write a little Python code that counts, the number of R's in the word strawberry and then run it and then give me the answers to that, right? So yeah, I mean, I wonder, how many problems within chemistry fall into that, right? Like, the models cannot understand graphs. They don't understand, graph structures because language is not really a graph, right? Like, it's mostly linear, even though you have like kind of, this attention mechanisms. But graphs are like very different kind of structures, right? I mean, I don't know. I'd be, curious, right? Like if we speculate, like, where the next, generation of models could be, like, is it because there's, like graph data in the training and other models have that native understanding of it, or is it because they use better tools or, I don't know, like, if you were, in um, OpenAI or Anthropic, like what would be your, kind of, path to get models to do better chemistry?
Mhm. Um, wow. I may or may not be trying to solve that right now as my research. um, I think, well, the short answer is I have no idea. Like, that's the honest answer. Uh, I think it's very tempting to. to come up with a solution that makes sense to us. But we're limited in our cognitive capabilities. So maybe it makes sense to let the reasoning model figure it out itself. Um, how do you navigate graphs effectively? I see that the latest models are multimodal and they can process images at the same time as language. And the latest, like 4.0, no, which one is it? 4.0 is it 04? Or 4.0. The 4.0 model
I had
is now off.
photo in the non-reasoning and then
Yeah, the
three.
4.0 model is so, yeah, actually, yeah. But the image generation is now like autoregressive within the uh, within the language model. So it's not a diffusion model anymore. It's like embedded. Uh, so there's something there that works for analyzing images. So maybe it's enough to learn, like actually train a model on graphs, some sort of embedding, and then reason about the embedding. Maybe using some sort of like graph tokens. I've seen some papers using like graph specific tokens. But then really, I think actually the harder question is what are we wanting these models to end up doing? And how do we quantify what success looks like? Uh, and then what does it mean to be able to reason better? So I think those are like the end result is what we actually solve first, and then how we get there will hopefully become obvious. I think maybe training on graph reasoning questions. I anticipate that like well graph problems are very standard mathematics and computing type questions. So I'm almost certain that OpenAI trained their models on graph reasoning. Like, what's the shortest path between 2 points? It's like traveling salesman type problems, you know?
Yeah.
And then that's transferred over into chemistry. That's what I expect has happened. So maybe training on natural language graph questions is enough. Maybe there's more efficient ways to navigate smile strings. Maybe we can teach models to speak in a different chemistry language that maybe doesn't make sense to us, but is complete and allows for valid reasoning. There's so many options here. I think the field's wide open, like for how to do this properly. But no idea. It's quite exciting, actually. It's the most exciting thing for a scientist is to have no idea and then just go and explore and see what happens.
Yeah, yeah, yeah. Uh, True. I guess like that's like if everything was settled, right? Like there would be little room for science, right? It would be like all engineering. How do you get the last 1% performance out of it, right? Rather than how do you drastically build something that you just couldn't do last week, right? Um, and you mentioned the kinds of things that we want these models to do. So why don't we talk a little bit about that, right? Like what do we want these models to do? Obviously, like we don't need language models to kind of tell us one name of a molecule converted to another name or whatever, right? Like so, what are the things that are really useful about this model that would like to?
Yeah, so the endpoint that I want to get to, I think uh, the computer scientists, machine learners, often forget just like how messy chemistry actually is. Uh, there's mess everywhere, and to summarize it all is quite difficult. But you think when you're running an experiment, you run an experiment given experimental conditions. So you have to write these conditions down and somehow consider these. You might be collecting evidence. So you've got multiple different sources of evidence combined together, like different experiments under very different contexts. Maybe you've invented a new experiment to do one specific thing. So you've got that. In drug discovery, uh, we've got things like everything's so conditional. So you create new assays that again, maybe you just invented the assay for the first time. So there's no other training data. You have like 10 data points you somehow make inference off of. Patents is a good one. So lots of literature. So you've got the journal literature, the patent literature, that's all contained in natural language. So like how do we extract that and then use that to solve problems? There's all of these pieces of information that exist out there that human chemists are able to navigate that are inherently noisy and messy, but somehow we're able to do it reasonably well. So it's all of those questions that I'd uh, like to solve. In my DPhil, the one question I'd really like to solve is along the lines of what molecule should I make next? So in drug discovery, you're iterating on ideas. You maybe made a few hundred molecules, and based on everything that you've seen in the past, plus all the public literature, plus maybe patents, uh, plus whatever other source of information, you have to somehow decide what molecule to make next. And the way that we've done this so far is, well, the way that most drug discovery companies work is that you have a group of chemists that work together and think, I like this one. And then machine learners' hope is that, okay, maybe we can do some sort of active learning, Bayesian something, and then like this molecule, that's a thin air. Uh, and I'm hoping for a different approach, one where we can, if we were able to extract all the relevant literature and chemical theory and physics and apply it all correctly, then maybe there's a natural language type of reasoning process where you can rationally go through and generate the answer. So maybe meeting at least the same level as a chemist and possibly being the same level as the best possible chemist. That would be quite nice. It's a big ask for a default, right? I've only got 3 more years, but maybe in a decade or so, or in a few decades, well, maybe it'd be next year. Who knows? The field moves exponential, right? Uh,
Hmm.
but at some point, that's what I'd really like to see is that these models being able to answer all of these really nuanced chemistry questions where there isn't a data set to train a model to do it.
Yeah. I mean, it's interesting, right? Because in some sense, that data is there. It's just contained in a form that is harder to use, right? Like, if it's on the research papers and in the literature, like you could somehow extract it and figure out another way or like a way to turn that into a data set that can be used for fine tuning a reasoning model, for example. I don't know, but I think the interesting thing is, well, I guess like if you somehow um build a model that has this chemical intuition of like, you did all these experiments, what is the next thing that comes in? You could use it to, I guess, to speed up, the work that chemists do in, drug discovery or like pharma companies,
Mm,
like, I don't know, like, all day. Where like, and I imagine like this is a very common kind of, thing that like professional chemists actually do, right?
mm. Yeah, one of the hardest things, I was speaking to a chemist yesterday, uh, someone that really knows what they're doing in drug discovery. And one of the really hard things is just keeping up with the literature. Like, there's so much literature that comes out nonstop. I was thinking of like this paper that came out from a group that I spent a bit of time in Edinburgh, and they've been able to understand a very specific particle molecule, phenol group, and how ortho substitution impacts a phenol. So it's new chemistry this is the first time I've heard about this chemistry, and it makes sense. They've done a really good job. It's like, right, this is the new chemical theory that might be in textbooks. But I only know that because I happened to see that paper, and most chemists won't have seen that paper. So a really helpful thing would be a model that is able to extract all the relevant literature and summarize it when you need it. So, like, here's a problem. How do I solve it? Well, what do I need to know to solve this problem? Uh, and some sort of like copilot or uh, equivalent of how ChatGPT is really helpful for coding and literature summarization. It's like, right, I need to go and know everything I need to know to solve this problem. How do I do it?
Interesting. Yeah, actually, it just came to me right now. Like, um, models are not really good at this in the programming side of the world either, right? Like, this is one of those things that happens all the time, right? Like, you tell the model generate code to do something, and then it uses external libraries, right? Like, it doesn't write from scratch, and then you run it, and then the external library says, "Oh no, this function was deprecated," right? Or
Mhm.
the library, changed. So maybe the equivalent of figuring out when people create new science, right, or discover new science is the language models that finally catch up to like what version of a library you're actually using it, right? Uh, and yeah, I mean, I don't think it's so. Like, I keep finding this error, all the time, right? Like, whatever. I mean, I don't know. Like, models are really good at creating, new code from scratch, right? Because they've seen that, a million times. You want to say, well, I'm using, all these libraries in my code, right? Like, I want you to write code against these libraries plus the rest of my code, right? That is, I think, a little bit harder, right? When people kind of, have breaking changes between versions or whatever, right? Sometimes it's not even well documented, right? So
Mm,
I guess, I mean, it's, of course, not as important, right? As like when people find new science. But in my mind, from the perspective of a language model, it's kind of a very equivalent problem, right? Like,
mm,
uh,
yeah. Although I think maybe science has a benefit that uh, it doesn't get depreciated, or at least shouldn't. Or maybe the typical case is that science, at least the underpinning like laws of physics, stay constant, and then uh, maybe
yeah,
if
but
you're
now,
fine
right?
tuning, like small things are changing on the surface level as the frontier expands. But then majority of chemistry stays relatively constant. Uh,
Yeah, I mean,
yeah,
I
yeah,
completely agree with you for chemistry, right? But I would say in medicine, you definitely see people discovering truly new stuff. Or like honestly, I mean, like this is not a happy example, but like there's been like instances of fraud, right? Like over the past few years, like there was this famous issue of like Alzheimer's, right? Alzheimer's data that was falsified, right? And like that sent a whole bunch of people, researching, areas
mm,
that made no sense, right? For many years, right? And it was found out that, somebody actually, had falsified, uh, plots or whatever, right? So yeah, I mean, like in theory, in science, you don't have that, right? But like, I guess in practice, there's still, become
yeah,
published things that are not true.
yeah. Well, that's the publication crisis is its own problem. I think I'm not going to solve that one. That's a big problem there.
Yeah, 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 yeah. And anyway, yeah, yeah, I think that's going to be a big challenge, right? It's like, human nature, right? More
Mm.
than a technical problem. Um, have you but like actually, let me ask you a slightly different question now. Um, like, are you worried in any way that these models will be able to kind of have dangerous applications? And I'll
Oh,
tell you why.
absolutely. Um, so I actually I'm quite disappointed in the big AI companies. So they've done a good thing. They've created the safety framework that says, if these models do this, that's bad. If a model can help someone reproduce a known chemical threat, so that's a known weapon. That's not inventing something new. It's like, right, here's known chemistry that people shouldn't be able to do. If you can do that, that's bad. That's tier three. We should release that. So they put that into their safety framework. And then the companies in their evaluation say, well, biological weapons are worse. So we'll only focus on biological weapons and ignore chemical weapons. I was like, you don't get to make that choice, right? You've established, like the quote from the OpenAI framework says something along the lines of like, releasing a model that can help reproduce a known chemical threat increases risk of chemical terrorism, right? It's a really serious statement. And then their evaluation is like, well, biological weapons are worse though. Okay, right. In a world, in a world where someone does reproduce a biological weapon, it would be bad, but it's really difficult, right? Or a lot harder than a chemical weapon. People can do chemistry in the kitchen. Biological weapon take a bit more effort. So there's a serious risk here of like releasing a language model that can enable someone uh, to do chemistry that they otherwise would have known. It's not like this chemistry is like a secret. Like synthesis of this is public, but having an expert, like a PhD level expert, guiding you step by step through how to synthesize a molecule, enables a novice to do chemistry that they wouldn't have otherwise done. So I did some like testing of these models as it came out, and O3, the day it was released, I asked it some questions that had to synthesize certain compounds that I really shouldn't, and it gave me quite some detail, quite some accurate detail on things that would have enabled me to do chemistry that would have led to a synthesis of a bad compound. Um, some of them are really bad. There's like Claude 3.7. Uh, I did very simple jailbreaking, and then all of a sudden it told me a full synthesis of TNT. And everyone knows how to make TNT. Like it's a standard chemistry thing, but it goes against their guidelines, and the jailbreak allowed it to do that. So I'm concerned here that the companies are just ignoring chemical threats, and it's not really acceptable. But I've tried to report my findings to the companies, and I'm not getting any responses. But they need to pay attention to it, at least to the same extent of paying attention to biological weapons, right? But they don't
Yeah.
seem to be doing it right now.
I mean, honestly, like I would be surprised, what they can do about biological weapons because it is very, very hard, right? You know, to figure out when somebody is actually taking, some viral protein and doing mutations of that viral protein to make it better for something else, right? I suspect, most experts, right? Like, if you're a biologist, right? And you get some random sequence and it says, make this protein, more, stable, for temperature. Yeah, no idea, right? Like, that may
Mm,
end up resulting in, you know, a, I don't know, a malaria parasite that
mhm,
survives, in cold temperatures or whatever, right? Which would be devastating, right?
yeah.
Um, so yeah, I mean, like they may say that they care that or that they worry about that, but like I'm not even sure that humans would recognize those things,
Mm,
with the naked
mhm,
eye.
yeah. I think, just based on what I read in their evaluations, it seems like there's a few public benchmarks for, biological threat production. Uh, I think it's possibly Andrew White has made some benchmarks on this. So the
Yeah,
public benchmarks exist. So they've just run those benchmarks and said, well, there we are. And they haven't put in the effort for chemical threats. There is, it should be noted that there is the AI Security Institute. So either AI Security or AI Safety Institute. There's one in the UK, one in America. They do additional safety assessments. So I do believe they check the chemical threats as well. But the companies are outsourcing this uh, safety testing to another institution. Which again, I don't think outsourcing it is the solution here. It should be part of like intrinsic within the company. They should be thinking about it, and it just doesn't seem like they are.
yeah. I mean, I'd be curious if you run your benchmark against Gemini. Like Google
Mhm.
is typically a lot better at this. And they typically have their safety filters a lot higher up. They they've been dealing with abuse or people trying to abuse the system for
Mhm.
far longer than anybody else, right? So
Yeah.
Google is typically very very good at that. Um, but so the reason actually I this the discovered is I was testing the uh like just playing a little bit with it the Ether Zero model that came from
Mm.
Future House, right? Andrew
Mhm.
White, favorite group, and I was asking a few relatively simple questions, and their model was basically fine tuned on a specific set of tasks. And when you deviate with those tasks, it doesn't perform as well. And one of the kind of failure modes is it thinks that basically anything that you're asking it is a chemical weapon. So I was asking it about like, yeah, I mean, I don't know that many compounds from the top of my head. Like, I'm not a chemist, but I was saying, can you give me a molecule, similar to, I don't know what I asked for, curcumin, right? And I'm doing that up.
Yeah.
Molecule.
Because I know I can't tell you. It's really dangerous. You just calm down. Please, no, no, caffeine. Yeah.
Yep, exactly. So I was asking, give me a molecule similar to curcumin, but like, a different property or whatever. I was like, I can't do that. It's a non-chemical weapon. I was like, I'm pretty sure it's not a non-chemical weapon, but
Yeah.
but anyway, yeah. So like maybe the kind of the safety filter was done to the max on that.
Yeah. Yeah. To be totally fair, though, I think being cautious is the way to do it. So I was really happy actually to see the filters kicking in at like quite a low threshold. Because I think it is potentially irresponsible to release a language model without thinking about this properly, especially it was a 28 billion parameters or something. So it's a big model they've released. So the fact that like, yeah, okay, it rejects a lot of prompts, but they've open sourced it, open weights it. Uh, so they've erred on the side of caution. And I haven't like scrutinized it in depth. So I'll do my best to break it and see if I can get it to say naughty things. Uh, but just, like, on the surface, it's good to see that they were putting safety as, like, a priority there.
Mhm, mhm. Yeah, for sure. I mean, I'm actually, curious, right? Like, about the going back the research direction that you mentioned before. If you take one of these open source models and then um, fine tune it on reasoning chains with graphs, with chemistry, can you get it to become much, much better chemistry, right? Like if you take um, I think Fuchsia House took Mistral, if I remember right. And I guess you could get, the DeepSeek model, for example, right? And which in turn, I remember, I think it was based on Llama. Wasn't it based on Llama? Uh,
The DeepSeek, they trained multiple versions using different base models.
mhm.
Uh, I don't know what the final DeepSeek R1 is.
Yeah. Oh, yeah. I think it was based on Quen, right? Which in turn
Yeah,
was based on
yeah,
Llama.
yeah.
Yeah. Oh, but I mean, I guess you could take one of this and say, well, let me extract um a few hundred, reasoning chains from chemistry literature, right? And then feed it to the model and see if it can come up with something, with something better. I mean, I don't know, like that wouldn't require, I guess, as much compute as training one of these models from scratch, right? And it may be
Mm.
good enough. I don't know, because I imagine I mean, I don't know about Oxford, right? But I imagine you don't have like, tens of thousands of
No, I read the Ether Zero paper, like 250,000 GPU hours. I don't have that. Nuh. So if anyone wants to give me a few, million GPU hours, I'd be very happy. But no, we don't have infinite resources. So I've decided that my solution is that I just have to do things on a smaller scale and think like try to be smart, try to like actually come up with innovative solutions, solve small problems well defined. That's what I try to do with ChemIQ. It's showing that right on these specific questions, we can do this. So this is a promising sign. So the next step will be something incremental, I think, uh, in the right direction. But I won't be solving the entirety of chemistry by December. Not yet. Maybe next December, but
you things can change a lot in a year, right? Uh and maybe that's a good segue, right? So like, what are some of the things or like maybe your favorite problems that language models or in general, but like, models are still cannot do well. And I'll tell you one that it was very surprising for me. I don't remember actually whom I was talking to. Uh but I think I was at the Stanford Drug Discovery Conference last month, a couple of months ago, and I was talking with somebody, and they mentioned, well, like we don't even have a great model to do predict the result of a reaction, right? And to me, like that was a strange, right? Like, again, I'm not a chemist, right? So if in my idea is like, well, this has to be more or less deterministic, no? Like you have your reactants and then you mix them in a certain way, and then like matter doesn't, come out of nowhere, right? Like, you know exactly, what your initial conditions are. Like, why can't you predict, what is going to happen on the other side? And they were like, no, we had no idea, right? Like, this is literally all over the place. Like, we didn't even know how to do it. And I was like, I mean, I didn't really understand it, right? But like, that's thought, okay, well, I guess there's still a lot of research to do.
mhm. Yeah, it's a reaction prediction. I'm actually terrified of reaction prediction because it's a really hard question. It sounds simple. It's like the most basic of chemistry, but no, it's hard. We do know a lot of chemistry, right? So you're right. Some reactions are deterministic. There's some like really simple, or not necessarily simple, but like we've got a way to think of it as like given these reactants, we expect this product. But the things that get more difficult is maybe if you've got multiple options for the product. So if it could react at multiple places, which site does it react at? Maybe stereochemistry or how fast it reacts, what yield you get. Um, there's lots of conditions that go into the reaction. So like there's a if you want to make a molecule, you do a thing called retrosynthetic analysis. So you work backwards, like this is how do I make it? Work backwards from what you're wanting, and each of those steps is very well defined. So a human is able to do it. Maybe it takes them some time, but a human can navigate backwards. But whether the reactions actually work in practice becomes a bit more complicated. Uh, just chemistry does a thing, right? Maybe a reaction that seems like it should work won't work because you've got a bromine somewhere in the molecule that falls off during the reaction, or there's this impurity that's inhibiting something. It just gets really, really messy really quick. Uh, so yeah, I don't think I'll be tackling reaction prediction. I think there's some other people out there that would do a much better job than I would uh, at doing it right. Certainly an interesting one though. I mean, it's the most fundamental of chemistry, isn't it? It's like that is chemistry of reactions. Uh, so maybe I should do it.
Yeah. Well, I mean, so like the other one is retrosynthesis, right? Like I imagine that would be even more interesting, right? Because like if you have that kind of synthesis path, like you can always like optimize it, either it's by hand or
Yeah,
whatever, right? But like, that's another thing that is like, in my mind, very, very different, right? Like, between, I guess a lot of other engineering and chemistry, or like in engineering,
mm,
if you think about like, well, I want to build this machine, right? Like build one piece at a time, and then you kind of, figure out how to do that,
mm,
right? Like in chemistry, sometimes like, like in theory, I guess like you could make anything, right? But then, how do you actually do it in the real
yeah,
world? Like that is very complicated.
yeah. Uh, yeah, once upon a time, I could navigate reactions. Not amazing, right? I was only ever an undergrad uh, when it came to this, but I used to be able to navigate it okay. And to the level of chemistry that I do, it becomes very complicated very quick. So I think PhD level and beyond, there's just so many possible reactions out there. Uh, but at the same time, though, pharma sort of restricts itself to only ten reactions. So the number of reactions in your medicinal chemist book is a bit smaller than maybe the entire space. Uh, but yeah, it's still hard. I still find it wild that a human can do it actually. Yeah. Like human, like, or can we do it? I don't know. It's pretty
I
impressive.
don't know. I was, I mean, I guess like I mean, I'm, again, like I think it as a computer scientist, right? Not as a chemist, right? Like, so, there was something that I heard, uh, David Baker, actually, Nobel laureate, last year, right? At a conference here in Seattle, and then he, of course, works on protein design, right? And one of the things that he was talking to the audience about was, can we design enzymes that then
Mm,
help us generate other proteins, right? Which is of course how nature does, I guess, photosynthesis, right? You kind of
mhm,
build a little enzyme, I guess, that catches one part of the molecule, and then you merge it with another part of the molecule. And I thought, okay, I mean that's brilliant, right? You don't need to figure out all this complex, reaction mechanisms that kind of, do all these things where you can't even predict what happens. You just design an enzyme that catches, half of your molecule, and then, the other half, and then you join it, and then you use ATP for it. And it's like, well, if you could do that, like, that kind of solves your entire chemistry, your entire, synthesis kind of problems. But I mean, I don't know, like, I imagine that is a very simplistic way to look at it.
I think, yeah, identifying that that's a simplistic way to look at it is fair. But I think also have had that idea as well. Like in an ideal world, biocatalysis is pretty cool. Like you don't need all of these expensive resources that are killing the planet to mine. You could print off your enzyme and then tailor this book. I think, well, I've got no idea what enzyme design looks like, but I do love directed evolution. So if you could design like a starting enzyme and then use nature to evolve it up until it becomes effective, and then but make that feedback with really quick. Right now, maybe 9 months. I don't know, but I think from what I hear, 9 months to do standard directed evolution to create a bespoke biocatalyst. Or maybe we could do that in like half the time by starting at a better starting point. I I have no idea. It's one of the infinite questions that I wish I could do. I think it'd be like enzyme design is awesome. Uh, I used to love biocatalysis. Uh, it's, I guess another question I wish I could do. Yeah.
Yeah, I mean, I think, yeah, and so right in the previous episode, which I can't really say, whether it will be next week or following, because I'm kind of, posting this, when, like between 1 or 2 weeks kind of interspersed. But right in the previous episode, I was talking with somebody about, this same idea of like, well, could we design enzymes that degrade, plastics or whatever, right? And I guess, when you use, I guess, directed evolution, it is I guess, relatively easy to do. Like you can do this in the lab, right? Like you can get plastics and bacteria that seek to kind of degrade it, and then kind of over many, many, many generations, just go ahead and pick the best. Um, a lot easier than I don't know, like I guess a lot easier than trying to do it in the environment or whatever, right? Or with a problem that is a little bit less well understood. I don't know.
Yeah, yeah. Enzymes, proteins are cool. It's just they can do so many cool things. Yeah. Maybe I should go back into structural biology. Half of our group does structural biology, and I just work in small molecule world. But proteins are wild. All of the wacky chemistry it can do and unlock. Like if you look at it, it's like wow, wow. Yeah.
Yeah. The small molecule world, of course, is like for drug
Small molecule is
discovery,
also
right?
beautiful. It's as small molecules are also wonderful. All of chemistry is wonderful. I love it all.
Yeah.
But
Cool. I was just looking at the time. I was like, "What else at the 1 hour mark?" I was like, the time went by so fast. But maybe kind of to end it, right? Like, what are something else that you're excited about, or something that we didn't mention, but somebody should go and do a little bit of research and learn a bit from, or like what else? What else is interesting?
what else is interesting? Well, that's a big question. What I would really love is for people to play with ChatGPT and just see what can it do. I think lots of people had the experience of trying to ask it questions a year ago, and it said lots of stupid things, and then they've sort of given up on it. But it seems like these models can now do really, really complicated things. For example, NMR elucidation. Uh, So what I would love is if people could go off and try and ask it other questions and see, does it get close? Does it seem to be roughly on the right track? It probably won't get the answer right. But there's so many like other parts of chemistry that I tried to do it all, but obviously I've forgotten it all, right? But like mass spec elucidation, like sort of EPR, uh, like maybe you can put in some raw data for isothermal calorimetry, like put just whatever experiment you're running, see, kind of analyze your data, kind of answer your questions. I'm not just saying like ask it a yes or no question or ask it a multiple choice question. Like actually give a really open ended thing. Like here's my data. What molecule is it? Or what conclusions can I get from this data? I'd be so interested to see what other people come up with. Uh, because really like that's the only way that we're going to figure out, like, first of all, like, what do people want to use these models for? And then how do we make them better? That's what I would love for people to do.
Awesome. Cool. And yeah, maybe one last thing, right? Like if somebody's interested in your research or reaching out or whatever, like what would be the best way to reach out?
So there's LinkedIn. I'm Nicholas Runcie on LinkedIn. Twitter is same. And then you can find my university email in my paper. So I think it's Runcie at stats.ox.ac.uk, I think. Uh, so one of those three. Lots of people are now bashing me on LinkedIn, so maybe your messages will get lost in the noise. So if you email me directly, I should see it.
Awesome. Well, thank you so much. It was a pleasure. I learned a lot. So thank you very much for taking the time to chat today, Nicholas.
Thanks very much for having me.